So let's look at some numerical methods of integration. Now, not every expression is easily integrable or maybe even integrable at all in some exact closed form. And so we have to resort to numerical methods in these cases. Now, numerical methods are an approximation. And they generally revolve around, for some curve, generally dividing the area up under the curve that we're interested in. So if we're interested in this particular curve here, f of x is 9 minus 0.1 times x squared, we want to find the area under the curve between x equals 2 and x equals 5. Well, these methods usually revolve around setting up a rectangle or a trapezium or something along those lines. And so this first particular method, the midpoint rule, involves dividing up the area concerned, so between x equals 2 and x equals 5, into rectangles, and then we can work out the area of a rectangle. And so the particular rectangle we're going to use here is this one. This for the midpoint rule, what we're essentially doing is making a rectangle here. Okay, we're essentially forming this rectangle here. Okay, now the base of the rectangle is 1 unit long from x equals 2 to x equals 3. So basically you've got a rectangle that is 1 unit long, and the height here, okay, and to work out the height we choose the midpoint of that interval, hence the dotted line there, the midpoint, and we ask ourselves, what is f of x at this value here? What is f of x? Okay, once we have that value, we have the height of our rectangle. Okay, this bit here will be f of x. So that's our f of x. Well, the area for this rectangle then is just going to be f of x times 1, or 1 times f of x, whichever order you want to do it in. It's just the base length times the height. Okay, notice with this rectangle we've chosen the midpoint of the interval between x is 2 and x equals 3, where that touches the curve, so that on the left here there's a little bit of the curve not covered, and on the right we've overcompensated because our rectangle goes above the curve. Okay, now that means there's some error. The numerical method is not as accurate as the exact integral because it is only an approximation. Okay, and how much we are under on the left and over on the right will depend on whether or not it's an under and over estimate of the integral. It will only be approximate. Now we can make this more accurate by making the intervals across here shorter. If we do that, then the wastage, the error here on both sides becomes less, and we get closer and closer to the exact value. Of course, in the limit, as the number of rectangles here goes to infinity, we get the exact integral. Okay, but for an approximate method, we have to choose some finite non-zero length. Okay, in this case we've chosen 1 unit. We could be more accurate by choosing rectangles that are half a unit long, a quarter, and so on. The smaller we get, the more rectangles we will have here, but also, and the more accurate we'll become, but also more work. So let's have a look here. Okay, well, we could take, if we're going to make an expression, because this is the area of one rectangle, now we have to sum this for every rectangle. Okay, so what we do, we need to start with the base length, and for this first rectangle here, the base length is A1 minus A0. That gives us the base length. That's this length here, which for our particular example here is 1, but it doesn't have to, it could be larger, smaller. Okay, larger will be less accurate result, smaller will have more rectangles and a more accurate result, and we'll get closer to the true value if we have a smaller rectangle. Okay, so how do we get this height here? Okay, well, that's the function f evaluated at the midpoint between a1 and a0. So if we take the average of a1 and a0, that's a1 plus a0 divided by 2, that gives us the value here. Okay, and then we plug that into our function, 9 minus 0.1 times x squared in this particular case. Okay, and that will give us the height here. That'll give us the value. Okay, that'll give us that value. All right. So the first rectangle, this one here, the base length times the height. Okay, second rectangle will be A2 minus A1, A2 minus A1, times again this height here. And that'll be f of A2 plus A1, A2 plus A1, take the average, divide by 2 to give us this value here. And so on. And we keep doing that for as many rectangles we have until we reach the very end. Okay, as a general rule, it's an minus 1, and the same in here, an plus an minus 1 over 2. And evaluating that, we come up with a value. So for instance, in this particular case now, if I scroll down, let's do it here now. F of x is 9 minus 0.1 times x squared. Okay, so the area is, and I should say approximately because it's not accurately, it's approximately, is 3 minus 2 times f of 3 plus 2 on 2. So 3 plus 2, the average of that is 5 divided by 2. Okay, so 5 on 2, which is 2.5. Okay, gives us the midpoint there. We put 2.5 into the function here, 2.5 into there, and that gives us the value here. So that's our first rectangle, plus 4 minus 3 times f of 4 plus 3 on 2, the average of those two. All right, plus 5 minus 4 times the function evaluated at the midpoint here, which is 5 plus 4 divided by 2, 9 on 2, 4.5. Okay, sum that up. Okay, and we get approximately 23.125 units square. Okay, I should point that out too. We should write that. Units square, whatever they are. It is an area after all. All right, let's have a look at the trapezoidal rule now. All right, now with a trapezium, so this one is there's a trapezium there. That length on top is A, that length there is B, this length here is the height. Okay, and then and we can also, it doesn't matter whether we tip it upside down either. Okay, there's a trapezium, the area there, A, B, this along here is height, and then of course your area for a trapezium is height on 2 times A plus B. Okay, and what we're doing here is with this, again with the same curve, 9 minus 0.1 x squared, just as an example, is that we're taking a trapezium here. This point here is a little bit lower than that point there, so you've got a shape like this, ever so slightly, a shape like that. Okay, and what we're doing is we're taking the same interval length here. In this particular case, it's 1. It doesn't have to be 1 unit long. Okay, and so we're getting, what we're doing here is we're doing B minus A to get that length there, divided by N, 2N actually. You'll see why it's 2N. And we're taking this height here, okay, that is f of x0, and this height on the right is f of x1, okay, and then the difference under here is b minus a on, whoops, n, okay, and then the area for this becomes, the area is b minus a on n, but we need a half of that. Remember over here it was the half here, remember the half? And then we need f of x0, I'll call it f0, plus f1, okay? And that's the height, that's the area of our first trapezium, f0 being f of x0 and f1 being f of x1. Okay, so that's our first one. And then for the second trapezium, we need f1, right, plus f2 in the brackets here. So f1 gets counted twice, which is why there's 2 of them here. Okay. Then we have b minus a on n. Okay, is that interval there, but we also need to times the whole thing by a factor of a half. Okay, so that gets counted. That's why there's a 2 there. Okay, and so on. And we just keep counting these trapeziums all the way along. And what we get is b minus a on 2n for all of them, outside f of x0 plus 2 lots of f of x1 plus 2 lots of f of x2, because one side keeps getting counted twice. Okay, so for the first trapezium, f of x1 was that side length there. Okay, f of x1. But then for the next trapezium, f of x1 is counted again, and then we have f of x2, and so on and so on. And we just sum up all these trapeziums, we add them together. We can do that for any interval from a to b, wherever we want to place this a to b here. Okay, so we choose a as x0, is 2 in this particular case, b is xn, is 8, and n is 6. We've got 6 rectangles here. And if we go down, working it out for our particular example here, the area integral 0 to 2 to 8 of 9 minus 0.1 times x squared integrated with respect to x is approximately equal to, and then we have 8 minus 2, b minus a, on 2 times n is 6 trapeziums, and then we have f of 2 as our starting point, 2 lots of f of 3, 2 lots of f of 4, and so on and so on. Put all those into the function, evaluate them. We get a half times here. 8 minus 2 is 6, over 6 cancels, left for 1 over 2 times, and then if you put those through a calculator, evaluate the function, you get these values, and we get approximately 37.1 units squared. Okay, and that is that.